In Chapter 11, we're going to be looking at alkynes. And alkynes are related to alkenes. They are similar, but they have some key differences. And we want to point out those differences and look at the kinds of reactions. We'll see that a lot of the reactions are very similar. So we'll start with what is an alkyne. And we know this already, but we're going to point it out. They do have a carbon-carbon triple bond. That carbon-carbon triple bond, so there's the carbon-carbon triple bond. The general formula of alkynes, if you have one alkyne, is CnH2n-2, and that gives us 2 degrees of unsaturation because of the 2 pi bonds. Terminal alkynes are alkynes that have the triple bond at the end of a chain. And internal alkynes are ones that are not at the end of a chain. They're within the main chain. And the reason that we differentiate between these is because there's a few of the reactions that will do different things or do something special with the terminal alkynes. And so I like to point that out, and we'll look at that as we go through this chapter. So a few of the alkyne structural features. There are 2 pi bonds and 1 sigma bond. This is something that we have talked about extensively before. The carbons are sp2 hybridized. They're linear. They have a 180-degree bond angle. And then here is sort of a representation of what those 2 pi bonds look like. The pi bonds are perpendicular to each other. So there they are, perpendicular to each other, and that the sigma bond is there in the middle. Now, in the previous chapter, in chapter 10, we talked about how pi bonds are not quite as strong, at least in the carbon-carbon bonds. The pi bonds are not quite as strong as the sigma bonds. And we even estimated how strong the pi bond was in something like ethylene. So if we take the strength of the carbon-carbon double bond, which is 635 kilojoules per mole, and subtract the strength of a carbon-carbon single bond in ethane, we got 267 kilojoules per mole. And that is a good approximation of what the pi bond strength is. And that indicates to us that the pi bond is somewhat weaker than our sigma bond. So our pi bond is somewhat weaker. Well, we can do something similar with an alkyne. So here we've got the strength of a carbon-carbon triple bond in acetylene, and we can subtract the strength of the carbon-carbon double bond in ethylene, and that gives us 2O2. And that would indicate to us that the second pi bond is weaker than the first. Now, one thing I want to caution you about is the second pi bond is not really weaker than the first. Both the pi bonds are equal in strength. When you have an alkyne, each of the pi bonds is exactly identical. So if we take these 2 numbers and add them up and divide by 2, that will give us our average pi bond energy, approximately. There are some things about this that are approximations. We don't need to worry about that too much, but we will find that our pi bonds are weaker. As a consequence, acetylene, or not acetylene, alkynes are more reactive than alkenes in general, and we'll talk about that and some of the sort of exceptions to that. All right. This is more of a curiosity. Cyclic alkynes. Cyclic alkynes are not very common. They not something you're going to find in like a natural product, or at least probably not. And the reason is, here I'll look. This is the smallest possible cyclic alkyne, and you can see there has to be at least 8 carbons in that ring for this to be possible. And the reason is because this is a linear arrangement, these 4 carbons that are the ones that are connected to the triple bond and the ones in the triple bond in a normal situation would be linear. Well, even with cyclooctane, they sort of bend out of that angle a little bit, so there's angle strain. As a consequence, cyclooctane is it's stable, but it's not going to be stable at room temperature. I looked up the recommended storage conditions, and the recommended storage conditions were at least down to negative 20 degrees Celsius with an inert gas over it to keep it from reacting with oxygen, and don't let it get exposed to light. So I assume you probably shouldn't feed it after midnight either. So, or wait, maybe that's gremlins. Anyway, it's not very stable. We're not going to spend much time. We have an example of one here in the nomenclature here in a little bit, but we're not going to spend much time talking about cyclic alkynes. Next, we're going to talk about nomenclature. So nomenclature for alkynes, it's similar to what we did with alkenes. We'll find the longest chain that has a triple bond. And so here, when we do that, obviously it's going to be this one that has, 8 carbons in it. We want to number the carbon to give the triple bond the lowest number. So we're going to number from the left side here. So 1, 2, 3, 4, 6, 7, 8. All right. And as far as where the position is, we count to which bond. So the third bond, which is the bond right after the third carbon, is where the alkyne is. So we would call this 3-octyne, or in the new system, oct3-ine. So we designate the location immediately before the ine, so oct3-ine. And then, of course, we put the substituents on. So this would be 6,6-dimethyl oct3-ine. So 6,6-dimethyl oct3-ine. If you have more than one triple bond, kind of like what we had with the double bonds in the previous chapter, we call those diines. Instead of dienes, we call them diines, and we use the suffix adiene. Just like we did with the dienes, we called them adiene. When we're putting the locations, we put those locations immediately before the diene. So after the A, but before the diene, and that is just how we're supposed to do it. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. So here we've got an octadiene, and the numbers are the positions. So right after the carbon 1, we have bond 1, and right after carbon 5, we have bond 5. So this is a 1,5-diene, and so we're going to call this octa 1,5-diene. And then if we've got triple bonds, we're going to call those triines, and we'll go ahead and name the substituent here. That's an isopropyl. So we have a 3-isopropyl octa 1,5-diene. So kind of rolls off the tongue, doesn't it? All right. In the scenario where we have a double or a triple bond, we're going to call that an ene-ine. So an ene-ine. The ene is for the double bond, and the ine is for the triple bond. All right. We want to number the chain to give the first site of unsaturation the lowest possible number. And it can be either the double bond or the triple bond. It does not have to be the triple bond first. So we would start here on this side. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a dec-ene-ine, and the positions for the ene are at position 1, and for the ine is at position 5. So it would be a dec-1-ene 5-ine. And then finally, we just need to put the substituents. We've got 2 methyls here at the 7 position, so that is a dimethyl. and a ethyl at the 4 position. The ethyl comes before methyl, so this would be 4-ethyl 7,7-dimethyl dec 1-ene 5-ine, which, you know, just a lovely name. And again, the reason we put the numbers immediately before these is just so we know that the 1 applies to the double bond and the 5 applies to the triple bond. So it is a very systematic way of naming. All right, if we have an alkyne substituent, for an alkyne substituent, we have a special name. If it's the carbon triple bond carbon with a hydrogen, we call that ethynyl. So ethyne is the name if it were, you know, acetylene, but we chop off that hydrogen and make it a substituent. We call it ethynyl. And so this particular molecule would be called ethynyl cyclohexane, and that would be the name. We don't have to put the number because there's only one substituent. So let's look at number 5 on the in-class assignment. So we'll switch over. There is number 5. All right, so on this one, we've got the name of the compound, and we want to draw the compound. So let's find our structure here. It is a cyclopentanol, so that's a 5-membered ring. All right, not a beautiful 5-membered ring, but that will do. And we've got a 2-ethynyl, so that's just like the one we saw a minute ago. It's the carbon triple bond carbon hydrogen, and an alcohol OH, and they are trans to each other. So I'll just arbitrarily put the OH here. So that would be carbon 1. And then to make it trans, we would have carbon triple bond carbon hydrogen, and we get the wedged line, or not the wedge, but the dashed line there. So that would be the trans 2-ethynyl cyclopentanol. One thing about this is that this has an enantiomer, so I'm just going to put plus enantiomer because it did not specify. It did not specify one particular enantiomer over the other, so I'll just put plus enantiomer. All right, so now for the 4-tert-butyl dec 5-ine. All right, so this one is a little bit challenging. We've got 10 carbons, so let's just start counting. So 1, 2, 3, 4, 5. So that's carbon 5 at the end. And now we're going to have a triple bond. And when you're doing skeletal structures, you just draw the line, and then you put 2 lines adjacent to it, and that indicates a triple bond there. There's an implied carbon that's here and here. You don't have to put dots like I did, but I did just for clarification's sake. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the dec 5-ine. And I will go ahead and number these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have a tert-butyl at carbon number 4. And so the tert-butyl is the one that looks kind of like a little chicken foot, except that one's upside down. So there we go. That is our 4-tert-butyl dec 5-ine. Pretty easy there. All right, this last one is not easy to draw. It is 3-methyl cyclo-non-ine. So non, of course, means 9, and so it's a cyclic alkyne. We don't run into these very often. The way I recommend drawing this is to start by drawing the 4 carbons associated directly with the alkyne. So we have a carbon that's single bonded to another carbon, a carbon-carbon triple bond, and then a carbon that is also bonded to that. So that's 1, 2, 3, 4 carbons. All right. And so we need 5 more carbons. And so I recommend it. So there's 2 of them. Go up, up, and then there. And I will number them because some of these are hard to see. We will number this. It doesn't matter. These are 1 and 2, just like in the alkene. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are the 9 carbons. And again, just like with alkenes, 1 and 2 are always the ones that are in the multiple bond, unless there's an alcohol, in which case that changes it. And then we have a 3-methyl. So we'll go ahead and just put a methyl there at the 3 position. All right, let's go back to our presentation. And we're now looking at the physical properties. So we're going to talk some about the physical properties and ways that you make it and things like that. So we'll do physical properties here first in section 3. We'll find that the van der Waals interactions for alkynes are very similar to the properties for alkanes and alkenes, and that's because we just have the van der Waals interactions, and we don't have any major dipoles, and we don't have any hydrogen bonding or anything like that. So we will find that they have low melting points and boiling points compared to polar compounds. That the strength of the van der Waals forces increases as the size gets bigger, and therefore the melting points and boiling points will also increase as we go to larger alkynes. And finally, we'll find that they are typically soluble in organic solvents and insoluble in water. So just like most of our alkanes and alkenes, very, very similar properties. When it comes to interesting alkynes, the one interesting one is the simplest alkyne, which is acetylene. 2 carbons and 2 hydrogens. It's really kind of a remarkable molecule. So H, carbon, triple bond carbon, H. Its official name, according to IUPAC nomenclature rules, is ethyne, but hardly anybody ever calls it ethyne. Even its mother doesn't call it ethyne. We call it acetylene. And so acetylene is what you've heard it as. It's a welding gas. You're probably familiar with that. So it is a colorless gas. It burns in oxygen, very, very toasty in oxygen, to form carbon dioxide and water. It takes less oxygen, and as a consequence, we'll find that when we burn acetylene in pure oxygen, it produces a very high flame temperature, typically around 3,100 degrees Celsius. And that makes it suitable for welding steel. By comparison, propane, which is a commonly used torch, that it's very easy to use. When you mix it with pure oxygen, it gets a flame up to about 2,800 degrees Celsius. And so that extra 300 degrees Celsius makes a big difference. And there are a couple of other things that advantages, some chemical advantages that acetylene has for cutting steel or welding steel. So there are alkynes that are synthetic hormones, and so related to some naturally occurring hormones, but that are synthetic. And so these have been proven to be very effective as oral contraceptives. And so that has had a big impact on our society. Kind of interesting. All right, here's another interesting one. This one is a chemical that is found on the skin of poison dart frogs. Now, the poison itself, this histrionicotoxin, I think I said that correctly. So histrionicotoxin It it is, like I said, it is poisonous, and it occurs naturally on the surface of these frogs. And it's not like super deadly. I wouldn't want to eat it or anything, but it does cause muscle contractions, makes it very uncomfortable. And I think from an evolutionary advantage, it makes it so that these frogs are less likely to get eaten by other animals. And also with their coloring, that makes them kind of warned off from certain predators. So kind of a cool chemistry. So that is histrionicotoxin. All right. So now we want to talk about the preparation of alkynes, and we saw this particular thing back in chapter 8. And that is if we have a vicinal or a geminal dihalide, that we can make an alkyne by using two equivalents of a strong base. And the two strong bases that we like for this are sodium amide and potassium tert-butoxide with DMSO as a solvent. And you can use either one with either type of dihalide. But these will do this will do two E2 reactions. So we'll get two E2 eliminations across the carbon-carbon bond, and we'll form these alkynes. So fairly interesting. So that is an important one to remember, because first of all, it's already been one that you have learned, and we're going to use this. We're going to use this in synthesis a little bit later. So now we want to look at how do we prepare alkynes from alkenes. Well, we know that we can prepare vicinal dihalides from alkenes. So if you halogenate an alkene, like this one, you'll produce this vicinal dihalide. Then if you treat it with two equivalents of the strong base, in this case the sodium amide, but you could have used potassium tert-butoxide, that would have worked great, you will produce a carbon-carbon triple bond. You'll get the two pi bonds on that same bond there. And so that is a method to convert something from an alkene to an alkyne, which that is kind of cool. All right, so just those are reminders on how we make alkynes. But we want to look at what can we do with alkynes? What kind of reactions do alkynes undergo? And so we're going to spend a lot of time talking about addition reactions. And so in most of the addition reactions, we've got some sort of compound that is usually an electrophile, and that electrophile reacts with the high electron density in our carbon-carbon triple bond, and we can get addition across it just like we do with alkenes. The difference is that we can do that addition 2 times. And in certain situations, we can even stop after one addition and form an alkene. Now, whether we form the trans or the cis alkene is going to depend on the mechanism. Remember, some of our addition mechanisms are syn, some of them are anti, and some of them don't have a preference. They can go either way. And in this case, we'll find that we can get E or Z product depending on what the mechanism is. So we do have a couple of different mechanisms similar to what we had with alkenes. So one equivalent with the reagent will give you an alkene, and then the second equivalent will give you the alkane. We saw a diagram like this for ethylene. And here, this is the one for acetylene, where the red represents an electron-rich region around the molecule. And you'll see that there is a perfectly symmetrical, cylindrical higher electron density around those carbons. Now, we tend to think of our pi bonds as being these two perpendicular things and that they're separate, but in reality, the electron density around this is cylindrical. So where one pi bond ends and the other begins is a little bit, well, it's hard to think of it that way, but we will get this cylindrical shape. This makes it so electrophiles can seek this out pretty easily. So if there's some electrophile, it can react with that fairly easily. So here are a few of the alkyne addition reactions that we're going to be talking about in this chapter. And we have another type of reaction that we'll talk about as well, but this is the heart of the rest of this chapter. So in the next section, we'll be looking at hydrohalogenation, and that's where we add HX across the carbon-carbon triple bond, except we can add it 2 times. And so we can get a geminal dihalide when we do that. With halogenation, we're going to add 2 halogen atoms across. Like with alkenes, we can really only do this with carbon or chlorine and bromine. We can't do it with iodine and fluorine. Just as a reminder, fluorine just catches everything on fire. So that won't work. So we'll do the halogenation. We'll talk about that here in a bit. With the hydration, remember with hydration we added H and OH across double bonds. Well, with triple bonds we do the same thing, but then something interesting happens that will cause the molecules to form these carbonyl containing compounds. In one case, a ketone, and in another case, an aldehyde. And we'll talk about those here in just a bit. So hydration and hydroboration oxidation. Before we move on to the addition reactions, there's one thing that I want to mention about terminal alkynes, and this makes terminal alkynes very useful for doing synthesis reactions. We can remove the hydrogen from a terminal alkyne, so from that end of the carbon, because it is a little bit acidic. And by a little bit acidic, I don't mean it's acidic like, acetic acid. If you put it in water, well, it's not even going to dissolve in water, but it will, you can't even deprotonate it in water, but what you can do is with certain very strong bases, you can remove it because the pKa of an alkyne is about 25. That means we just need to have a base whose conjugate acid has a number bigger than that. And just as a reminder, 2 such strong bases would include the amide ion and the hydride ion. So amide and hydride, the pKa of their conjugate bases is in the 30s, and that makes them perfect for deprotonating alkynes to form what we refer to as the acetylide anion. And it turns out that acetylide anion is a really good nucleophile. It's a strong nucleophile. It is a strong base, so we have to be careful not to accidentally put something that we can deprotonate in there, but it is a strong nucleophile, and it is quite possible for it to react with an electrophile. So I have a generic electrophile here. There are a lot of options for that, and we're going to be primarily interested in using it in SN2 reactions. All right, so let's start with hydrohalogenation for our addition reactions. We can add 1 equivalent of a hydrogen halide across the carbon-carbon triple bond, and that will give us a vinyl halide. So here we've got our carbon-carbon triple bond. We add 1 equivalent, and we get the vinyl halide. And then we can add a second equivalent. Usually we just put them all in there at once, and it reacts, and we go all the way to this, and we don't ever isolate this. But if you want to isolate this, you have to put 1 equivalent in and probably do a separation because you'll get some of this anyway. But that is how we can make a geminal dihalide. And this is interesting, it always ends up being geminal. We don't get vicinal dihalides this way. Kind of interesting. So we'll always get a geminal dihalide. All right, so now let's look at hydrohalogenation and does it follow Markovnikov's rule? And the answer is yes, it follows Markovnikov's rule. Remember the rule for Markovnikov when we're adding a HX across a carbon-carbon double bond, the hydrogen goes to the carbon that has the most hydrogens. Well, in this case, we'd have to have a terminal alkyne, and the hydrogen will go to the carbon that has the hydrogen. And then the halogen will end up going to the other carbon. So here this carbon has one hydrogen on the end, and you'll get two hydrogens after the first addition, and then after the second addition, you'll have three hydrogens out there on that terminal carbon, and you'll have a geminal dihalide. And if you're clever and you set it up properly, you can do one addition across the carbon-carbon triple bond, and you can get a vinyl chloride. And that vinyl chloride, there are interesting reactions we can do with that, including making what's called polyvinyl chloride, PVC, which is a commonly used polymers for things like pipes. All right, so let's look at number 9. We're going to switch over to number 9. All right, we want to draw the organic products formed when each alkyne is treated with two equivalents of HBr. So let's count up the carbons, 1, 2, 3, 4, 5, 6. And when we do two equivalents of HBr, we're going to get Markovnikov addition. So we'll get two hydrogens going to this carbon, and we will get two bromides going to this carbon. So it will be a dibromide. All right, so it'll be a dibromide, and 1, 2, 3, 4, 5, 6. And that would be our product, adding HBr across that. All right, for this one, Markovnikov's rule doesn't really help us here because this is an internal alkyne, and with internal alkynes, it could go either way. So we're either going to get, and I will number this for clarity purposes here, 1, 2, 3, 4, 5. We're either going to get both hydrogens going to carbon 2 or both hydrogens going to carbon 3. Wherever the hydrogens go, the bromines are going to go to the other atom. So this is going to give us two different products. We'll either get the 2,2 dibromo or the 3,3 dibromo. So 1, 2, 3, 4, 5. So the 2,2 dibromo, oh, that was ugly. All right, just bear with me for a second. There we go. So we'll either get the 2,2 dibromo or the 3,3 dibromo. All right. So, and then with this one, we've got ethynyl cyclopentane. So ethynyl cyclopentane. On this, we will find that the hydrogen is going to go out to this terminal carbon, and then the bromine is going to go to this carbon. So again, we're going with two equivalents. 1, 2, and then that is going to have two bromine atoms on it. So this carbon had 1 to begin with, and now it has three hydrogens on it. And then this carbon has nothing else attached to it, and now it's got two bromines attached to it. So we did double addition across that carbon-carbon triple bond. Now, you may be wondering, why is it that we always get geminal dihalides? Why don't we get vicinal dihalides? Why is it that the halogen always ends up on the same carbon as the first halogen? Well, let's look at the mechanism. So the mechanism is going to look very similar to what we did with alkenes. We're going to start off with adding hydrogen. The hydrogen electrophile is going to react with that carbon-carbon triple bond, one of the pi bonds, and the hydrogen will immediately go over to the carbon that has the hydrogen already, and here we form a vinyl carbocation. Now, we have not discussed vinyl carbocations yet, but they are not quite as stable as our typical. Would be a secondary vinyl carbocation. It's not as stable as a typical carbocation. As a consequence, we'll find this first step is a little bit slower than it is for alkenes. Our second step is that our nucleophile will come in and react with that vinyl carbocation, so it'll go to that vinyl. And then we've got vinyl halide, in this case vinyl bromide. And in our third step, we're going to do addition again. Markovnikov's rule still applies here. So the hydrogen goes out to the carbon that has two hydrogens already, and we'll form this secondary carbocation, but it has a bromine on it, and we're going to talk about that one here in just a minute. That bromine makes a difference on that carbocation stability. And then in our fourth and final step, this is very similar to what we saw in step 2 and what we've seen in the previous chapter on hydrohalogenation. In that fourth step, the bromide is going to come in and react with the carbocation to give us the geminal dihalide. So the key as to why we get a geminal dihalide, for this it makes sense because of Markovnikov's rule. But for an internal alkyne, we still get geminal dihalides. And so the reason that we get those geminal dihalides, I'm going to tell you on this next page. All right. So hydrohalogenation of alkenes is slower, and I mentioned that because our vinyl carbocation is not quite as stable as a typical carbocation, and as a consequence, it's more difficult to form that, and we'll end up with a higher transition state. Okay, so that's not a big deal. When it comes to doing that second addition, so again, here we're getting Markovnikov addition, the hydrogens going to the carbon with the hydrogens, but there's something special about this thing, A. And that something special is that when we form that carbocation, there is an additional resonance structure for that. And that additional resonance structure, because we have an atom with lone pairs that is directly adjacent to the carbocation, we can share those electrons to make a pi bond between, and again, it's a resonance structure, so it's a combination of these two. Here is our combination of these two. Here is our hybrid structure. What that does is it spreads that positive charge across both the carbon and the bromine. So it spreads that positive charge out. And by spreading that positive charge out, we can end up getting a more stable carbocation. If the carbocation goes to the other carbon, we don't get that. Now, we wouldn't expect this because of Markovnikov's rule, but again, with an internal alkyne, we'll still observe this, which is why we always form the geminal dihalide. All right, let's look at number 10. Switch over with our document camera here. Number 10, and this is an easy problem. I wish all problems were this easy. Actually, no, if all problems were this easy, then just everybody would take the class. I just want people who want to take the class. So here we go. We're going to share that electron density, the lone pair, with this bond. So we're going to go from the lone pair to the bond. And in doing that, we'll draw our double-headed arrow that we use for resonance structures. And we'll have the double bond there, chlorine. I'll go ahead and put the remaining electrons, and just as a reminder, we now have a positive charge on that chlorine. And in the average structure, we spread the positive charge out over the carbon and the chlorine. The real advantage of this particular resonance structure is that it gives everything a full octet. This doesn't have a full octet on the carbon, but this, everything has a full octet. It does put a positive charge on chlorine, and chlorine is fairly electronegative, so that's a little bit unusual. But again, everything has an octet, so that's an advantageous resonance structure. Let's do the same thing here. All right, we're going to take the pair of electrons that's on the oxygen, and we will share it with this bond to make a pi bond. CH3, oxygen, double bond, CH2, and so we still have a lone pair there on the oxygen. If we look at the formal charge, we'll have a formal charge, +1 on that oxygen. All right, last one here, and it's a little bit difficult to see, but you can see there's a positive charge on this carbon. If you download the sheet, you'll be able to see it a little more clearly, but there is a positive charge on that carbon, and we have a lone pair of electrons on that nitrogen. So we're going to go from the electrons to that bond. And in doing that, we will create a double bond in that resonance structure. As a consequence, we'll see that the nitrogen ends up with a positive charge. And again, just like with these other two, it gets rid of, or it gives us a better resonance structure because that better resonance structure, everything has an octet, and that helps to satisfy that. All right. Well, I think what we're going to do, I think I'm going to end the video here, even though it's about 40 minutes. I'm going to end the video here, and I'll start up the second video with halogenation. So go back over here, and like I said, we will start with halogenation on that next video.